Welcome to this week's High Energy Seminar. We have two speakers today who are talking about things related to X-ray binaries. They're both finishing grad students. The first speaker today is Kristen, Dage. She's a grad student at Michigan State University, where she's working with Steve Zepp. She got her bachelor's degree from the University of Michigan in Dearborn. And she's worked on a number of different X-ray binary related problems. She's worked on SMCX1. She's looked at LMXBs in Andromeda spiral galaxies. And what she's going to be telling us about today is ultraluminous X-ray sources in extragalactic globular clusters.
So I want to talk about these ultraluminous X-ray sources in globular clusters, so what they are, why we care about them, and what we've been doing with them. So just the usual definition of a ULX is they're non-nuclear X-ray sources, point sources that are accreting in some kind of X-ray binary situation, but their X-ray luminosity is above the Eddington limit for a 10 solar mass black hole. So stuff that's 10 to the 39 ergs per second or above. So when you're this object in this really luminous binary, your compact object can only be one of a few things. The first can be a massive stellar or intermediate mass black hole, but it's accreting at sub-Eddington rates, so it can get very bright, but it's kind of boring. The next option is you can have a bunch of neutron stars or black holes together. So they're sub-Eddington. Individually, they're not that bright, but add up enough of them and they could be bright. It's also not super interesting. But the last option is super cool. It could be a black hole or a neutron star that's accreting at these super Eddington accretion rates. And so that means there's this new and different regime of physics going on that we don't know much about. So most ULXs, including all of those that have found to be neutron stars, which is really unexpected and exciting, they've been found in star-forming regions of galaxies, like this example here. I think this is M82X2. And so the studies that have been done for donor stars of these systems indicate that they have high-mass, hydrogen-rich donor stars. But by contrast, you actually can find a handful, only about 10 so far, that exist in globular clusters. And these ones are not associated with star-forming galaxies. They're globular clusters associated with elliptical galaxies. So this is a very different environment than the other ULXs. And so we expect them to have pretty significant differences. The two main and most interesting ones is that globular clusters are older populations. So that means that your donor stars, you're not going to have massive hydrogen-rich donor stars available to accrete from. You're going to have white dwarfs and older stuff with less material. But the other thing I find really interesting is that the way binaries form in globular clusters is completely different than the ones in star-forming regions. The ones in star-forming regions are field sources, so the two objects will co-evolve together. But when you're in a globular cluster, there's stuff moving past you, and actually something else I found out really interesting is that binaries in globular clusters preferentially exchange. So if there's two objects in a binary and something more massive passes by, the object can swap out for the more massive star. So the formation histories of these systems are really interesting. So why do we care about them? And so there's one of the main things has to do with the driving question of do black holes even exist in globular clusters? And so there have been some successful studies of searching for black hole candidates in Milky Way globular clusters. Those techniques don't really work when you move outside of our galaxy. The two main studies involve looking for very low luminosity stars, low luminosity X-ray sources. And then there's another group that will study every single star optically. They'll get optical spectra of every single star, all the stars in the blob, and study those. And that seems kind of painful. But the thing is, we can look at the extragalactic ones, so hundreds of thousands of globular clusters, and we can search for ULXs in them. And then this can help us understand the numbers of black holes in extragalactic globular clusters. So like I said, it's like we're really curious about can we find black holes in globular clusters, because previous works in the 1970s suggested that as soon as the black holes are formed in the cluster, because we do expect them to form in the cluster, clusters are old and they're great places to form black holes, but they would just, because of the dynamics, they expected them to just get completely kicked out of the cluster. Newer simulations are showing that this might not be the case, and then Geezers et al. 2018 is the first paper that actually did a dynamical measurement of a black hole in a globular cluster in the Milky Way. But kind of the overarching picture here is that one of the places where the progenitors to the LIGO black hole merging sources could have formed could be globular clusters. And so to start to tackle this problem, we really need to understand the number and the natures of black holes and globular clusters better, and especially extragalactic ones, because the Milky Way only has less than 200 globular clusters. And when you go out to other galaxies, you know, there's hundreds of thousands of clusters available to study. So the way we do this is we, for different galaxies, we have a list of the positions of globular clusters, and then we just match them up with high luminosity X-ray point sources. And so the ones that match, we follow up on in more detail in X-ray, more detail in optical especially. And so I did this. Oh, wow, I forgot to put this slide in here. So there is another major potential issue here, which is that how do we know that the X-ray sources that we're looking at in these globular clusters, how do we know that it's really all just due to one X-ray binary and not a bunch of other X-ray sources put together? And to illustrate this, I have these two pictures here. The upper one is an X-ray image of 47 Tuc, which is a beautiful cluster, and you can see it's got all these lovely X-ray sources here. This is what I look at. This is a source around NGC 4472, and I have a point source, but there's all these X-ray sources in there. So there's a few ways we can consider this problem. The first is that if you have variability on short timescales, then it's unlikely that all of your luminosity is just coming from adding up a bunch of stuff. Another interesting point is that the typical total integrated X-ray luminosity for a Milky Way globular cluster is 10 to the 36 ergs per second or less. That's the equivalent of the error bars on the ULX measurements. So whatever's going on in these clusters that they get above 10 to the 39 is like not what you would expect, and it's very unusual. And then the third point, Greg Sivikoff in 2007 published a paper that said that the number of low mass X-ray binaries hosted by a globular cluster scales with its color or metallicity. So the more red the globular cluster is, the more low mass X-ray binaries you're going to have in it. So the cluster really has to be very, very red to host enough low mass X-ray binaries to add up to 10 to the 39 ergs per second. And most of the clusters we've been looking at are not that red. All right, so these are the sources I've been looking at. So there are 5 persistent globular cluster ULXs across 3 galaxies, NGC 4472, NGC 1399, and NGC 4649. And one of the questions we wanted to ask with this is, do the globular cluster ULXs show spectral variability that corresponds to changes in their X-ray luminosity or not? And we found that the sources were best fit in X-ray either by a black body disk or by a power law. So what we did for all of them, I fit all of the available data, and I plotted the X-ray luminosity on the y-axis, and then on the x-axis here, I plotted the power law index. This is what it looks like for the ones that are best fit by power laws. I don't know what's going on here either, but the ones that were fit by disks are really cool. So in this plot here, I have the X-ray luminosity on the y-axis. On the x-axis, I have the inner disk temperature. And what we see is that for sources with lower characteristic temperatures, the best fit temperature value really doesn't change that much, but there's a huge spread in luminosity for both of them, the purple one and the orange one. And then the sources going on up here don't show that behavior. It looks like they're either clumpy, or there's that one that looks like it shows a LT to the 4 relationship. But this gets really, really interesting when you look at their optical spectra. So we have optical spectra for a few of these, and this is what it looks like. It's very busy, and I'm sorry about that. But the one here that looks like it follows the LT to the 4 relationship, this is its spectrum. So all you're seeing is the spectrum of the globular cluster continuum. It doesn't really have emission beyond that. But the other two, the top one, the orange one, has O3 and N2 emission lines. The purple one, which is very special, has this really interesting and broad oxygen emission line. For the rest of the talk, I'm actually going to focus on RZ2109. So it's in a globular cluster associated with NGC 4472. there's about 6,000 globular clusters in NGC 4472. Actually, about 5 of them host ULXs, but RZ2109 is the best studied, and it was also the first one discovered. And Macron et al. 2007 published a paper with this XMM light curve, and what you're seeing is that it has this variability on short time scales. So within a few hours, the count rate has a huge drop. And so because you have this strong variability, it implies a single object, and then it's also high luminosity, about 4 times 10 to the 39 ergs per second. But it's really, when you get to the optical, it's what makes it so fascinating. So this is its optical spectrum. So what you're looking at, the blue line and the red lines are 2 spectra. One is from Keck, one is from HST. And then the black line is a fit to the globular cluster continuum. And so there's just this huge amount of very broad, very luminous O3 emission beyond the cluster continuum. As of right now, this is the only source that has an optical spectrum like this with this broad O3 emission. So it's really unique. And then some other measurements were done to place constraints on the hydrogen emission, and there's not much, or there's really no hydrogen emission beyond the globular cluster continuum. So the only binary companion that can produce this type of spectrum with a lot of oxygen and no hydrogen when being accreted implies that we're maybe looking at a white dwarf in the system, which is really cool. Another thing to note about the emission spectrum is that it has this really interesting complex. So it has, it's a doublet emission, so there's 4959 all the way over there on the left, and then there's 5007. And the 5007 has an emission core, and then it also has a blue shifted wing and a red shifted wing. So we've actually been studying this over the past 10 years or so, and we found that the structure changes over time. So we added up the flux in each of those components, and what's interesting is that it goes into a long-term decline over time, but then our most recent observation, which was taken in April 2019, the whole, especially the core seems to rise, but the total equivalent width in the structure goes up. So what we're not sure of is this representative of short-term changes near the central engine of the source, or is it representative over like large-scale changes averaged out over like an oxygen nebula? I'm really interested in these spectra, and I wanted to show you guys them one at a time. So I made a little movie of the change. Well, it's a fake movie. But anyway, this is the first spectrum that was taken as a Keck spectrum from 2007. I didn't use it in the earlier analysis because it's a lot lower resolution. So just keep that in mind. So it goes up in 2009. In 2011, it decreases. 2016, it decreases more. It gets very faint in 2018. And then 2019 is where it rises again. And then just to show you again, you can see that it has this decline and then rises again. And then what's interesting is that in the 4959 doublet emission, it follows the same pattern of getting fainter and then getting brighter. That was really weird and unexpected. So the kind of bigger scale question that we want to ask here again is, how do the X-rays and the optical tie in with each other? So we have this plot. This is all of the X-ray luminosities that we've measured off of it for over 20 years in the upper panel. So it has time on the x-axis and the X-ray luminosity in the upper panel. The lower panel is the equivalent width in that oxygen line. So in the oxygen, you can see that it's been declining for the last 10 years, and then our last data point shows it getting larger. And then with the X-rays, you can see that it has this variability on all sorts of time scales. The X-ray points I'm most interested in are these 3 orange ones from XMM up here. So those were all taken about 2 days apart. So what you're seeing is that it drops an order of magnitude or more in X-ray luminosity with only about 2 days. We did have a Chandra observation that was taken quasi-simultaneous with our last observing night, as well as some SWIFT data. And it's faint, so it seems like this is indicative of there must be a lag between the X-ray and the optical, at least on short time scales. So there is a really nice Milky Way analog for RZ2109, the source called 47 Tuc X9. So 47 Tuc X9 is a candidate ultra-compact X-ray binary. It's a black hole candidate. It's in the Milky Way globular cluster. And Miller-Jones et al. 2015 suggested that it's a black hole candidate. Baramian et al. 2017 found they measured a 30-minute orbital period in its X-ray spectrum. And then in the X-ray spectrum, they also saw evidence of oxygen emission. And then Tudor et al. 2018 found no hydrogen emission in the source. Now, RZ2109, again, it's a black hole candidate. We have the oxygen emission in the source, and then no hydrogen emission. So the only major difference between these two is about 6 orders of magnitude in X-ray luminosity. No big deal. And there's a really good paper by Ross Church published in 2018, and he worked through like dynamical formation of a black hole and a white dwarf in a globular cluster, and found that it's actually really hard to get a stable formation of a white dwarf and a neutron star binary in the cluster, but you are likely to get a white dwarf plus a black hole. He also said that RZ2109 might be like a younger version of 47 Tuc X9, so that would be cool. And then in the last few minutes, I want to talk about a little bit of new things I've been doing. So I really am interested, like I said, there's only 9 persistent globular cluster ULXs. There's one that's not persistent, so that's not very helpful to me to study. And so I'd really like to look for more of them. So I started looking in M87. M87 has really been nicely studied. There's been a lot of optical surveys of globular clusters in there. There's a ton of Chandra data, and then it's home to about 15,000 globular clusters. So that's really exciting. And the Chandra data I've been going after, especially because there's so much of it. I found about 28 Chandra observations that have 15 kiloseconds of data or more. And I just ran wave detect on them to get all of the X-ray point sources. Now, one of the things I had to be careful of is that really annoying black hole and jet in the middle of there. But thankfully, the jet is narrow, and so I just fit a line across where the jet is and rejected anything close to it. But then I went through about 28 observations, so I still had to like cross-match all of the X-ray sources and then cross-match my cross-matches. But I came up with about 70 unique sources. About 12 of them are ULXs. So all of the X's on the plots, the pink in the wider field one over there, the pink stuff in the middle is the jet. The X's are all just X-ray point sources. The squares are all ULXs in every single observation. That blue star in there is a source that has the highest X-ray luminosity. So in this histogram, this shows all of the X-ray luminosities. And so there's a source that's about persistently at 8 times 10 to the 39 ergs per seconds over there. And I'd be really interested in following up on that and seeing, like, what is its optical counterpart? Is it a background AGN? Is it in a globular cluster? You know, like, what is it? And then I've also done some matching of the other ULXs to lists of photometric globular cluster candidates and spectroscopically confirmed globular clusters. And I found a couple of matches that I'd really like to follow up on. And even the one that's spectroscopically confirmed, I do have a very low quality spectrum of, but there's this tantalizing hint at optical emission. So I'm really curious about that one too. And that's all I have.
Well, this is fascinating work. Congratulations on this. I do have a couple of questions. We've been looking at these sources that are soft and ultraluminous for a while. And what you have here is the first time I've seen in an external galaxy being able to follow the optical emission as well. So your source is pretty soft. How soft was it in terms of what kind of KT you were getting?
0.1 keV. So it's like it's not as soft as like the super soft ULXs, but then it's
just on the boundary between super soft and quasi-soft.
Yeah.
Now the super soft sources that we know of, where we've been able to do this, have a definite correlation. It's actually an anti-correlation between the optical and the X-ray, and the time scales that you see in terms of the variation in X-ray are kind of like exactly what you see there. I don't think anyone has looked locally at this O3 emission, because locally, not being in a globular cluster, you've got a lot of gas around. And so you've ionized a large region, and you won't see the short-term variability. In that line, you see it, in terms of the full optical magnitude. But I think this is a fascinating possible connection to follow up on, and you'd be showing that these soft sources, whatever it is that makes them so soft, is behaving the same way in your environment as the local ones.
That would be
So
really
you'd
cool.
have another local analog. Is 47 tuck X9 a soft source or a hard source?
I'm not sure what its
That
X-ray
would be
spectrum is.
interesting to
Yeah.
know. That might be another difference in addition to the 10 to
Yeah.
the 6 orders of magnitude. Yeah. Thank you.
Actually, for NAD7, how much you can resolve it to what a center of NAD7?
I've actually,
The radii.
I'm not sure what you mean by that.
I'm just saying that how much deep you can see this emission, because according to the orbital motion of the stars, you cannot go further than 200 parsec. I mean, closer than 200 parsec. I want to know whether you have seen any emission inside of that radii or they are all outside.
The globular cluster in M87 that's the most promising is actually very, very far away from the galaxy center.
How much far?
Like maybe 8 degrees. So it's nice because I don't have to worry about the hot gas.
Wait a minute. So these are actual pictures of the sky, right?
Yes.
I just mentioned a declination.
Yep.
Right, so that shows basically M87 and where this source is. Right?
Yep.
Yeah, so it's 0.3 of a degree away. If I'm reading that correctly.
Well, somebody, I think I cropped it out to make it fit, but somebody for some reason decided to study a field up and to the right, so it's hiding in there.
Oh.
I'm not sure why they did that, but I'm grateful to them.
Any other questions?
Are those actually bound to M87, or are they really just bound to the cluster as a whole?
Well, you can measure the radial velocity if the cluster's in there associated with M87.
Hmm.
Any final questions?
The 70 cell sources that you detected in M87, those all came from individual observations with outside units?
Yes. Well, so there's about like 400 detections, and then when I match, there's 70 unique ones. So now I know their variability too, if they vary.
You might want to look in the China source catalog page.
Okay.
Because you do stack observations there if they overlap.
Yeah,
And you might get better sensitivity.
that's a good point. Thanks.
Okay, let's thank Kristen again. So our next speaker is Konstantina Anastasopoulou. How'd I do?
Well.
She's finishing PhD student at the University of Crete, working with Andreas Apis. She got her bachelor's from the University of Patras in Greece, and then her master's degree she actually got from the University of Munich, where she was working on Cepheid stars. She's been a visiting student here at CFA for the past roughly year, so kind of a familiar face. And today she's going to be telling us about an XMM survey of star-forming galaxies in the local universe, looking at X-ray binary simulated relations.
Okay, thank you, Francesca. Can you hear me? I guess yes. This project has been in collaboration with Frank Haber from the MPE, Andreas Zezes and Konstantinos Kovlakas from the University of Crete. To start with a small introduction, studying normal galaxies in the X-rays, galaxies not containing an AGN in their center, has revealed that their X-ray output is dominated by the collective emission of the X-ray binary population in the hard X-rays and from the diffuse gas emission in the soft X-rays. You can see an example here. This is the interacting star-forming galaxy up to 99. This is a Chandra color image. And you can see the X-ray binaries as point sources and the diffuse gas emission in red. Since high-mass X-ray binaries represent younger stellar populations, one would expect that they would trace the star-forming activity of the galaxy. And since low-mass X-ray binaries represent older stellar populations, one would expect that they would scale with its stellar mass. Indeed, such scaling relations have been identified since the Einstein era. Here we show some of the most recent examples. This is the plot from the work of Mineo et al., and it shows how the luminosity of the X-ray binary population scales with the star formation rate of the host galaxy. And here we saw how the luminosity of the X-ray binary population per star formation rate over the specific star formation rate scales in the work of Limer et al. However, since these works have been based on a few dozens of galaxies, there are still some open questions. For example, there is poor characterization in the low specific star formation rate regime, and there seems to be some amount of scatter for the low star formation rates and the high specific star formation rates. The question is whether this scatter is an observational effect or it represents differences in the X-ray binary populations themselves, like age or differences in the age or the metallicity. We did see similar variations when we studied these two star-forming galaxies in subgalactic scales. So this is NGC 3310, which you can see color Chandra image. This is, it shows a peculiar morphology as a result of a recent merger with a low metallicity dwarf galaxy, which triggered the formation of this circumnuclear star-forming ring and two spiral arms. This galaxy hosts a large number of ULXs. The same case is for NGC 2276, which is very interesting since it's a member of a loose group, and its west side, which you can see here, which also hosts the most bright ULXs, is compressed as it moves through the intragroup medium. This you can see better in the optical image of the galaxy. You can see its disturbed morphology. What we actually wanted to see, since we see some morphological variations and we have indications for differences in the X-ray sources, we wanted to study this in a more quantitative way. For that reason, we put the different subgalactic regions on the scaling relations. Here you see, for the case of NGC 3310, the luminosity of the X-ray binary population per star formation rate versus the specific star formation rate. This is the reference fitting line of Limer et al. And what we see here is that all these regions that fall above the scaling relation are all subgalactic regions containing ULXs. All these regions are subgalactic regions that do not contain ULXs and on average agree with the relation. And the galaxy itself, its total luminosity, also agrees with the scaling relation. In the case of NGC 2276, we see that the west side of the galaxy, which contains the most bright ULXs, the subgalactic regions are also above the scaling relation, and the galaxy itself falls above the scaling relations. We find that this deviation, this excess we see, is not the result of stochastic effect, and it most likely reflects differences in the ages of the stellar X-ray binary populations, since these subgalactic regions are associated with younger stellar populations in the galaxies. This motivated us to study the scaling relations on a much larger scale. For example, the studies so far contain a couple of dozen of galaxies, which firstly is a small sample, and secondly does not reflect the conditions, all the star-forming conditions in the local universe. Ideal for this study is XMM Newton, in order to calculate the integrated emission of galaxies, and also because it has performed many observations on nearby star-forming galaxies, either pointed or serendipitously. We also use the Hecate catalog, which I will explain a bit more later on, which is the most complete galaxy catalog in the local universe, incorporates robust distance and stellar population parameters. And this sample provides us the opportunity to cover the full range of star formation rate and stellar mass in the local universe. So a bit more about the Hecate catalog. This is a project led by a fellow PhD student at the University of Crete, Konstantinos Kovlakas. The primary purpose of this catalog is to serve as the basis of investigation of X-ray emissions in nearby galaxies. Therefore, it contains all galaxies, all known galaxies observed within a volume of 200 megaparsecs. It uses as its basis the Hyperlida catalog and contains various information on major minor axes of galaxies, position angles, age and contact, as well as photometric information and stellar population parameters from various catalogs like SDSS, GALEX, 2MASS, and so on. Here you see the distribution of their distances, and also here you see the distribution of the galaxies in the star formation rate stellar mass plane, and we see that we cover more or less 5 orders of magnitude in both star formation rate and stellar mass. We then cross-correlated the Hecate catalog with all available XMM Newton observations, which resulted in about 2,400 observations and a bit more than 3,000 galaxies. We used the standard analysis pipeline provided by MPE to calibrate the observation and produce images in the 5 standard XMM bands. We removed high background observations, but kept observations that cover the galaxies at least partially. This resulted in almost 2,300 observations and almost 3,000 galaxies. You can see here the distribution of our distances. We see that we have more or less a uniform coverage up to the maximum distance of the catalog. And again, here is the star formation rate versus stellar mass plane. You see the distribution of the galaxies. The blue points is the Hecate catalog, the full sample, and the red points is the XMM sample. We see that it's representative of the distribution of the star formation rate and stellar mass in the local universe. We then continue with the photometry. We performed aperture photometry on all our galaxies. The size was the size of provided by the Hecate catalog, folded with the PSF of XMM. For extremely faint sources, we use the BER tool in order to calculate probability distribution for the source fluxes, taking into account the variations in the background and the local intensity. And then we use the count rate to flux conversion using the model flux tool of Chow, and assuming an absorbed power law model of photon index 1.7, typical for X-ray binaries, and galactic absorption. Here you see a typical example of how an image would look. This is a composite image of XMM with the 3 detectors, and you see here we have 3 galaxies. Then we continue to the spectral analysis and fitting. So we fitted spectra for for about 1,700 galaxies. And imagine most of the galaxies have multiple observations, so we're talking about lots of spectra. Here you see some indicative examples. We see that we have all kinds of qualities, from very noisy to high quality spectra. This is a powerful tool because it allows us to measure the fluxes more accurately, but also we can identify AGN, as you see here, that have not been identified before with other methods. In more detail, we use the SEPA fitting package. We fit the 1,700 galaxies, which is about 6,000 spectra. This has resulted in 1,200 galaxies that were fitted well with an absorbed power law model plus 1 or 2 thermal plasma components. You see a typical example here. And about 300 galaxies that had more complex spectra and were typical for AGN. You see a typical example here, where you see a prominent iron line at 6.4 keV. We then calculated fluxes and luminosities at different energy bands based on the best fit model of each galaxy and accounting for model uncertainties. from now on in this talk, when I talk about fluxes, in the case of sources that have multiple components, I will be talking about the power law component of the spectrum, since we are interested in the X-ray binary population. And then, since we had the spectroscopic fluxes, we could test the reliability of the photometric luminosities. You see in this plot here that the luminosities resulting from the photometry and those from the spectra are in a very good agreement. However, there is a small excess in the photometric luminosities. So for that reason, we apply a correction statistically to our sample in order to account for extra absorption and thermal gas contribution. We then used the star formation rate and stellar mass from the Hecate catalog. The star formation rate resulted from total infrared luminosities based on IRAS and WISE measurements, and the stellar mass from KS band luminosities based on 2 mass measurements. We then identified the AGN in our sample using different methods. We used BBT diagrams, spectroscopic surveys, X-ray identification surveys, as well as visual inspection of our own spectra. This resulted in 72 non-AGN galaxies, which you see here with the yellow dots. We should note here that this is a very conservative sample, since we used galaxies that we had some kind of information on their AGN contact. And these are our first results. Here we plot the luminosity of the X-ray binary population versus the star formation rate of the host galaxy. And this is the fitting line of Mineo as a reference. We see that our galaxies follow the same trend, however, there is an offset. If we also include the extremely faint sources, effectively the upper limits, we see that the trend remains. But we also wanted to see if this offset is a result of some bias introduced from differences in the X-ray binary populations. For that reason, we have used the criterion from Limer et al., wherein the luminosity versus specific star formation rate scaling relation, galaxies with specific star formation rate above this value, 5 times 10 to the minus 11, are dominated by the high mass X-ray binary population, and those below by the low mass X-ray binary population. Putting this in our scaling relation, we see with red color the low mass X-ray binary dominated galaxies, and with black color the high mass X-ray binary dominated galaxies. What we see is that both populations follow the same distribution, so we cannot attribute this offset to this behavior. What we actually think is happening is that this offset is a result of the way the luminosities have been calculated in the Mineo relation. What they actually do is that they integrate the luminosity function down to a limit of 10 to the 36 ergs per second. This leaves some amount of unresolved X-ray emission, which is unaccounted for. In our case, we use an aperture to calculate the total emission of the galaxy, which accounts for the total population. Indeed, this difference leads to about an offset of 0.3 to 0.4 offset. A proof for this explanation is actually the fact that we do not see this offset when we plot the hardband luminosity and as comparison the Limer relation, who in their work have used the same approach as we have calculating the integrated luminosity of galaxies. Then we plotted the luminosity of the X-ray binary population per star formation rate versus specific star formation rate, and using as a reference line the Limer fitting line, and we see that we have a very good agreement. However, since by construction our sample includes only star-forming galaxies, we lack galaxies in the low specific star formation rates. So as you can imagine, this data set is a gold mine for X-ray studies of nearby galaxies, and in our immediate plans, We want to compare with X-ray binary population synthesis models, compare with the Chandra Nearby Galaxy Survey, construct scaling relations of the hot gas of galaxies, calculate average spectral properties of star-forming galaxies as a function of their star formation rate and specific star formation rate, provide an AGN library, and study the AGN demographics. To summarize, I have presented the most extensive X-ray survey of nearby galaxies containing about 3,000 galaxies. It covers 4 orders of magnitude in the star formation rate and specific star formation rate. We have photometric analysis for all of them and spectral fits for about 1,700 of them. We provide scaling relations with the star formation rate, specific star formation rate, which is in good agreement with previous works. Thank you very much.
Does the galaxy catalog include dwarf galaxies?
I don't think so. We lack in, because we would have covered this low specific star formation rate.
The reason I actually mentioned it is that some of them have very high specific star formation rates and some of them lower. It seems to vary, so I thought that would be an interesting comparison to make. And one other question about concentrating on the star-forming galaxies. So you have the snapshot at whatever time we're looking back at, but that galaxy may have existed for a long time in the past and have had time to develop an LMXB population as well. So how do you think about that? That there could in each of your galaxies be a less prominent contribution from the LMXBs that because of this great distance you can't separate out?
Yeah, to be honest, the most reliable way to account for this is to also include the stellar mass in the scaling relations, so that we can account for the luminosity of the X-ray, of the low mass X-ray binaries. But from the plots I've showed, where we see the luminosity of the different populations, low mass and high mass, we don't see a significant amount of excess in the low mass X-ray binary population. So this is something we need to investigate more, but we don't see a significant contribution, let's say.
Well, that might even be interesting because it may be telling you something about the star-forming history of
Sure.
the galaxy. Thank you.
So very nice talk. I want to thank you for giving an amazing advertisement to the fact that you can use Chandra data analysis tools on XML.
I know. I was expecting that from you.
It seems like even after you're correcting for the specific stellar mass, you still have a very broad distribution. Do you have any, pretty clearly there's some other phenomenon going on that's driving variation in that. Do you have any ideas as to how you might go about trying to quantify what the additional sources of variation are?
Yes, we need to, there are many sources of variations that contribute to these variations, like galaxies containing ULXs, like M82 cases where the ULX is contaminating, let's say, the whole luminosity of the galaxy. We're thinking about that. We want actually to quantify the scatter in this scaling relation. We have information, for example, on metallicity. We could see how this would affect this kind of variation. But yeah.
It seems like it might be a way of hunting for ULX holding galaxies.
Yeah, it could be.
I had one question. So it looked like initially there were a lot of low specific star formation rate galaxies, and those all disappeared because of the AGN copies?
Yes, yes. Yeah, we lose a lot of galaxies, especially because we select the AGNs through BPT diagrams. Yeah. And for most galaxies, we don't have information. So.
Oh, okay.
So there's a large
amount. Where you're not sure.
Yeah, there's a large amount of galaxies we're not sure what they are, so we don't use them at all.
Any other questions?
How do you turn this off?